Hi, everyone. Good morning, everyone.
There you go. Good morning, James. How are you?
I'm doing very well. And so thank you so much for inviting me. We'll get started in just a moment. It's a pleasure to be here at PyData Festival Amsterdam. We really wanted to hold an in-person PyData Amsterdam this year. Unfortunately, we weren't able to owing to the current circumstances, but I'm very glad that through the hard work of Matthias and Mauricio, we were able to do this event. And so I think even though they can't hear you, hopefully those of you watching at home can give them a little round of applause to thank them for all of their hard work putting this event on. One of the upsides of that is going to be that of all the PyData events, PyData Amsterdam will have maybe the longest unbroken record of conferences, and so they will get their kudos in the end. Now, today I want to present to you a topic that you may have heard people talk about a lot, optimization of Python, how to make Python code fast. I gave this talk that's a very tedious title, Furious and Fast Python 7, just to reflect on a very tedious movie series that you've probably seen before, probably fell asleep in, and I'm sure you've had the exact same experience when watching optimization talks. In just a moment, I'll share my screen with you, and then we'll get started. Now, just a note, this is a talk, and it's a novice level talk, and so unfortunately, I don't have much workshop material. I'll just be presenting for you. Now, you can see my screen behind me. In just a moment, I'll hide in the very corner of the screen just so you can see everything, and we'll get started. The title of this talk is Furious and Fast Python 7. We're at PyData Fest Amsterdam. It's Thursday, June 17th, 2020. It's my pleasure to be here presenting this material to all of you. Now, I will note that it is 3 a.m. for me in New York, and so I really must enjoy coming to speak with all of you if I'm willing to stay up this late to present for you. I'm James Powell. If you like this talk or you're interested in similar material, you can follow me on Twitter at don'tusethiscode. I give quite a few talks at different PyData events. Unfortunately, this year we don't have as many PyData events, but I'll be speaking again, most likely at PyData Global, another event that Matthias is involved in later this year. As I said, this is a talk, not a workshop, and it's novice level. So hopefully this talk might give you a new framework or a new way to think about things, but it may not tell you anything that you might not have seen before, just to get you ready for what you're going to see. Now, it is the case that when we talk about Python, everybody wants to write fast Python code. It seems obvious that this is something that you want to do. And you might ask yourself once, why? Like, why do we care about writing fast Python code? Is it because it's scalable? I guess that kind of makes sense, because we could say that if we're in a business context, there's always this competitive push, this capitalistic push to grow. And if our code isn't scalable, then it can't grow. And so our business will find some business model by which it can make money. It'll try to scale that up. That's the nature of what a business is. And so scalability is very closely tied to that model. But I don't know if that's as compelling, because you can see, your code may not be the factor that actually matters in the scalability of some system. You could say, well, because it's performant. And I would say this is probably a very bad reason, because this word performant is just a terrible word. Please don't ever use it. It's probably the worst word you could probably come up with. What does it even mean? And you could say, maybe one of the reasons why people really like to make their code fast is because it's measurable. If I say, oh, I wrote some code and it's really easy to read, it's not really measurable. It doesn't seem objective. But if I say, oh, my code runs in 3 and your code runs in 5, well, that's definitely measurable. So I think for a large degree, when people talk about writing fast code, it's often just because this is a measurable thing that they can do on their code. And they're oftentimes ignoring other more important factors in terms of the readability of the code, the extensibility of the code. In a moment, we'll talk about one clear problem when people talk about code and the speed of code. And we'll see how, just because this is a measurable unit that measures one snapshot in time doesn't necessarily make it a very good measure of the overall quality of your code base. Now, unfortunately, irrespective of the reason why you might want to make your code fast, Python is slow. And we're told Python is slow, and we get very excited when we first learn Python, and then we realize, oh, this is so slow. It's so much slower than all the other tools that I use. But whatever. Seriously, this seems to be the complaints about the speed of Python often seems to be just something that is very easy to complain about, just like people like to complain about the global interpreter lock. It seems more of a lightning rod for complaints than any very serious, substantial complaint. And the reason that I might say that is, if you look at some very, very high performance systems, things like GPT-2, they're written using TensorFlow or PyTorch. They're written using Python bindings. And so you can see things that are very performance sensitive still have some element of Python to them. And so this idea that Python is slow and that's the end of the story and you should just go and use something that's faster seems to be missing something very significant. Now, one important question when we talk about fast code is, do you really want to write fast code, or do you want to write fast enough code? And I think oftentimes when people try to aim for performance, what they really want is they want code that's fast enough to get a certain job done. There's a hidden bar that they're trying to hit, and past that bar, it's not really that meaningful for them to go any further. And you'll see that when we actually talk about typical mechanisms by which, or typical processes by which people do optimization. Now, one of the problems that we have when people talk about optimization is they talk about it as a static process, but in reality, when you're talking about optimization of real-world code, it's really a dynamic process. And here you can see we're leaning into our static-dynamic dichotomy a little bit hard, but just to break down these terms for you, you might think that if we're talking about a static process, we're talking about looking at a given piece of code at a fixed time, and we're trying to make it faster. So we're saying the code as it exists today, let's see if we can iterate on it and make it faster. Whereas the reality of code bases is that they're part of a dynamic process. In reality, we don't want to make the code faster today. We want to take a given piece of code and make it faster over time. If our code is fastest today and then becomes the slowest code tomorrow, that's not desirable for us. In a very similar sense, oftentimes when we talk about design problems or we talk about characteristics of code bases, we're often talking about them in a snapshot view. We're talking about them statically. We're saying, if we take this fixed problem in space and time, and we try and figure out the best way to model it, what is the best way to model it? But in reality, an actual code base is part of a dynamic process. It's part of a software development process. And this software development process is fundamentally dynamic. In other words, you're given a requirement on day 1, and you're given many requirements on day 2, day 3, 3 months later, 6 months later, 1 year later. Similarly, your code starts with some smaller set of cases that it has to solve. 3 months later, 6 months later, a year later, the number of cases that it has to solve, the size of the data sets it has to process are very different, and the dynamics of those may be significantly different. As a consequence, things that you might do on day 1 to lead to writing what you think is the fastest code may not survive until day 365 or day 1 of year 10 of this code base. Now, it is important that we contextualize this idea of optimization in the terms of the software development process. We really have to think, how is software actually written? And what we really need to do to approach this topic better is to come up with a better framework, a better way to consider what it means to optimize code, what it means for code to be fast. And so what I've prepared for you in this talk is a framework that might help you try to put a little bit of substance behind these discussions of optimization and discussions of how we go about making our code fast. And I call this framework the MISSA framework. The M stands for measurement, the I stands for intuition, the S stands for structure, the other S stands for specialization, and the A stands for acronym. And in fact, the second to last S actually stands for stupid, because this is a very stupid acronym. And in fact, it's not even an acronym, it's an initialism. So really, this is the MISSI framework. Now, let's start with the first letter of this framework, measurement. It is obviously the case that if we want to make our code fast, we have to perform some measurement. We have a limited amount of time, and in that limited amount of time, we have to decide where we're going to spend that time to change some code in our code base. And so it doesn't make sense for us to try to micro-optimize every single line of code. It makes sense for us to measure, to use those measurements to guide ourselves, but that's not really about the code itself so much as about our dynamic in the software development process. In other words, it's about we have finite time and finite resources, and how do we best exploit those finite resources? Because if you did not have finite resources, if you had an infinite number of programmers working on your code base, there really wouldn't be any value for measurement. You would just try to optimize every single aspect of that code. Now, you may have heard a 3-step process for a software development process that situates this idea of optimization near the end. You may have heard people say things like, make it work, make it right, make it fast. In other words, first make the code actually work, make it do something. From a business perspective, this is a good idea. You know, if the code doesn't work at all, then it's not really valuable making it fast. If the code isn't correct, then that it's fast might not be valuable either. And so you first make the code work, then you make sure the code is correct, you make sure the code is giving you the right results, and then you perform optimizations. This is a framework that you might have seen in reference to comments about optimization from folks like Dijkstra. Dijkstra was famously somewhat bearish on optimization as in a practice, because he said, look, if the code is not correct, who cares how fast it is? Now, in a business process, that's not always really the case for how we approach or look at our code. Instead, if we really think about what we do, we oftentimes kind of make it sort of work, and then we make it fast, and then we sort of check to see if it's right, and we don't do any of these processes just right. So I think that 3-step framework is missing some realities of how we go about writing code. Instead, what we might do is we might start with some measurement. And there are many, many measurement tools that we might use. You may be familiar with sampling measurement tools like PySpy. A very popular one that I've seen that's led to some very interesting examples of optimizations is Scalene. And with these tools, we might make micro-optimizations. We measure some code, we identify some hotspot lines, we go into those hotspot lines, we make micro-optimizations. We rewrite those lines or some subset of those lines and improve them. But there's a problem with this process, and a very significant problem, because when we do that, we're looking at this code as a static entity. We're not looking at it as a dynamic entity. Let me give you an example. Fundamentally, when we look at a code base, that code base is subject to an execution environment. That execution environment may change over time. I'll give you a canonical example. I myself have no software and no computer science background. I have an electrical engineering background. And I started writing code on microcontrollers. And in microcontrollers, there's a certain fundamental aspect that doesn't carry over to the kinds of computers that I write software for. In other words, in microcontrollers, there was a memory versus CPU dichotomy. And every time the code was kind of slow, we leaned on our memory. We'd write lookup tables. But that approach doesn't work anymore. It doesn't work for our standard mini computers, for our desktop computers, and for our servers. Now, we lean towards the CPU. We say, you know what, memory access times are so slow that it's sometimes better to do redundant computations at CPU than to pay for a lookup table, because the slowness of accessing anything past L1 cache is not worth the time. And so you can see that fundamental dynamic changes over time. A consequence would be, if I, in 1992, wrote some code trying to make it the fastest in the world, and I used a lookup table, come 2004, 2005, it's no longer to be the fastest in the world, because this fundamental dynamic has changed. Now, that may seem like a very broad point, so I want to give you a more concrete example, a real-world example that you might see. And this is, I think, the only one example that is participatory in this entire talk/workshop, which is the following. Let's say we have some code, and that code creates a data set, and we have some function that operates on that data set. And we need to apply that function to every element of this data set. Now, set aside that in practice you probably would use NumPy for something like this, but let's say we do this in pure Python. And we have a couple of options. In one option, we might have a list comprehension. In another option, we might use the map built in, and we might pass it to the list value constructor. In another option, we might use that map built in, and we might use this unpacking generalization in order to pass it, in order to construct a list, to build a list from this. And another option is we might just skip the function entirely and just inline this and just write a standard list comprehension without any function call. Which of these is the best? This is the only participatory part of this. This is the only question I'll ask you. But here I've given some names for these. And in the Discord channel, if you'd like, try to put in order from fastest to least fast. FC, the function in a comprehension. LM, list with this map built in. MU, this map with the unpacking syntax. And LC, the straight up list comprehension. I'll give you about 15 seconds. And the reason I'll only give you 15 seconds is you don't need to noodle on this for too long. And the reason you don't need to noodle on this for too long is the result may surprise you. You may be able to get the fastest, but you're not going to be able to go too much further. Let's take a look. Now, it's actually surprisingly easy for us to test this. And for some of you, 15 seconds might have been enough time to actually try this. You know, Docker Hub has versions of Python from 3.5 to 3.9. You can run a Docker container. You can run this code using the time it module in the standard library. You can give it some number of loops to run, and you can actually write some code like this. And this is what I actually did in preparation for this talk. It took me about 10 minutes to do. And I want to give you a disclaimer before I show you some of the results. The disclaimer is as follows. I didn't look that closely into the Docker files, so maybe the different versions of Python are being built with slightly different options. I didn't really pay attention to all of those. We do know some details of what happens when Python runs in Docker. We may have seen the news recently that there are certain security modes that are active inside the Docker container, which cause our Python interpreter to be significantly slower than what's outside the Docker container. Setting all of that aside, because it doesn't really matter for the analysis we're going to see, I also want to give you a couple other important points. Just for your reference, I ran this on my Surface Pro, and I pinned my CPU frequency, and I am using an Intel P-State governor, and I'm running it on AC power, and there was nothing else running at the same time. And those are the typical caveats we see about these kind of benchmarks. And the most important caveat is, I don't care. Like, seriously, we're going to see that this benchmark doesn't matter, and all those caveats and all that qualification doesn't matter. But I'll tell you something important. I actually do care. I very much care. Because if I didn't care, I wouldn't be here. I really do care, and I really hope that you're enjoying the talk so far. Let's take a look at those results. Hopefully you had enough chance to try and guess for yourself, and let's take a look at what the actual results are. In Python 3.5, the list comprehension is the fastest option, the pure list comprehension. In fact, in every single version of Python that we tested, the list comprehension is the fastest. when we get to the intuition section, we'll see why. It should more or less make sense. But if we exclude the comprehension from that and we look at all of the other options, what we see is the function call in the comprehension is fastest in Python 3.5. And then in Python 3.6, the list map is fastest, and you can see it is significantly faster. This is a meaningful performance difference. In Python 3.5, it's not that meaningful performance difference, but in Python 3.6, now it is a fairly meaningful performance difference. It's a couple of percentage points. In Python 3.7, it's the same, but suddenly in Python 3.8, the unpacking in the map is the fastest. And in Python 3.9, we see that same behavior, but there's not enough noise. There's not really enough signal there between these last two options of Python 3.8 and 3.9, but you can see consistently for all the runs I did, this changed. Fundamentally, if we made a choice in Python 3.5, that would not have survived until Python 3.9. In other words, a major question would be, which of these do you choose? Well, this is actually very problematic. I need to figure out which of these do I choose for the Python version. And I certainly am not going to choose 4 of them and have an if sys.version.info equals 3.5, do this one. If sys.version equals 3.6, do that one. That modality, that checking is going to drown out the speed of the underlying function itself. It'll add an enormous amount of noise and mechanism to my code base. Nobody ever does that. In fact, when people actually do micro-optimizations, what do? They look at the current version of Python that they're using, they see which is the fastest, and they delete all the previous versions. And as a consequence, if the version that they thought was the fastest is no longer the fastest over time, and you see from those measurements, just a very simple, very small structure across 4 very, very similar versions of Python, we see a dramatic change of which is the fastest and which is the slowest, and there is a dramatic difference between the fastest and the slowest. The choice that they would have made would have been wrong, and they would not have ever been able to tell because they would not have preserved the previous pieces of code. That's somewhat surprising. How would you even track this over time? I mean, you definitely, even if you thought, oh, I want to make sure this is always the fastest, let me keep all 4 versions. Maybe new variants could come up. Well, that's not such a big deal. But how would you even track this over time? That would be very difficult. And you can think this question of which version of Python might you have used to write this? Like, maybe I should just use the latest one. I should write all my code with the fastest using whatever the head version of Python is, Python 3.9. But then that doesn't include the possibility that my users might be using Python 3.5. How do I even figure out from this matrix of options which is the ideal option? How would you even systematize this? It's unfortunate, but there's no real way for us to include any kind of structuring information in our program for us to have the program itself dynamically choose which of the 4 is the fastest. Ideally, if we had a very, very smart compiler, you could tell it declaratively, this is what I want to do, and it could figure out which of these is the fastest. But that level of structuring information and that level of smartness of the compiler is way beyond what we've seen in Python. And to a large degree, it's even way beyond what we've seen in most languages, other than languages that have query optimizers like SQL. In fact, a more serious problem would be, what if we were using a tool like Pandas? And Pandas has a lot of fast paths. So we might have chosen the fastest approach, and then suddenly Jeff Reback adds another fast path to Pandas. And the fastest approach that we chose, that was some contortion, that was uglier than the stupid, dumb approach that we measured using Scalene or PySpy as being slow, is now faster because they added a fast path for this dumb code. One surprising thing you'll find when you actually try to optimize Python code is dumb Python code ends up being fairly fast. And one of the reasons for that is, well, dumb Python code probably pops up a lot in performance benchmarks. And because it pops up a lot in performance benchmarks, it probably draws the attention of the core developers. Because it draws the attention of the core developers, they then go and optimize those paths. And so you have this kind of perverse behavior where your attempt to optimize may be confounded by the attempts of core developers to optimize. And you have this perverse behavior where somebody adds a fast path, and your code that you thought was fastest is no longer fastest. Now, what you might say is, that's not a big deal. I'll just add regression tests. So I'll just add a little test to my code base, and I'll just test to see if it gets slower over time. And that might be a meaningful thing to do. You might actually have caught in the test results that Python 3.9, for whatever reason, is actually slower at some of those benchmarks than Python 3.8. Maybe that's because, as a RC build, they haven't added some optimizations in. Maybe Docker Hub was building it slightly differently. I'm not sure. But if you think about what that regression test would tell you, it wouldn't tell you what the fastest is. It would just tell you, did my code get slower? So in practice, you weren't writing the fastest possible code. You were writing the fastest enough possible code. The regression test implicitly tells me that what you really cared about was my code fast enough to meet some benchmark, to meet some baseline of performance? And as long as it stays at that baseline, I'm happy, as long as it doesn't diverge from that baseline. You didn't really care about, was this the fastest code ever? You just cared, well, is it the fast enough for my use case? Well, if that's the case, was it really that important for it to be fast for your use case? Maybe you should have gone back and really understood is this the important thing that I should be spending my time on? Now, before we go any deeper in talking about this business side, I want to talk about intuition. Because when you look at that example, you might say that's kind of a silly example. That list comprehension without the function call is always the fastest. And it's always the fastest by a good margin. And I have some intuition. And my intuition guides me to saying, you know what, between some of those other options, maybe it's not as meaningful. But clearly, I know the fastest option. I'm always going to pick the fastest option. And so this game that we play here across different versions of Python doesn't really affect that one pure list comprehension without the function call example. And my intuition would have guided me correctly, and I wouldn't have fallen into this trap. So let's talk a little about intuition. We can see that is absolutely the case in all of our versions of Python. Now, if we compare Python 3.5, we can definitely see the comprehension without the function call is definitely faster by a significant margin than anything else. And so it was somewhat artificial for us to exclude that from our consideration. Now, let's try and figure out why that might be. And what we might do is we might write a very simple piece of Python code. 3 functions, one called FFF, one called GGG, and one called HHH. FFF calls GGG, GGG calls HHH, HHH doesn't do anything. We just call FFF. And what we might do is we might run our Python interpreter under GDB, and we'll put a conditional breakpoint. And we'll put a conditional breakpoint on the actual function call. We'll look for a PyC function type. We'll actually see if it's that HHH function, and we'll try and put a breakpoint when that HHH function is actually invoked by our Python interpreter. And we'll see that at the C level. And so we'll put a breakpoint on PyObjectVectorCall, which is our part of our Python interpreter that handles function calls. So this is the C function that handles the calling of Python functions. And so combined with this conditional breakpoint and the breakpoint here, and the code as it's written here, we should have everything that we need to just kind of see what happens when a function is called in Python. Now, bear in mind, this program does not do anything interesting. It defines 3 functions, and it calls them. And that you should see 3 function calls that, serially performed. And that's it. Nothing else that's interesting. This is the stack trace that you get. This is the stack trace that you get from that. You can't even see what's on the screen. There are 31 C stack frames corresponding to a simple dummy Python program that does 3 function calls. 31 C stack frames. Well, if our intuition is that Python function calls are slow, this is pretty good evidence for that. 31 stack frames. And if we remove some of the noise from that and we look at a smaller subsection of this, this is approximately a subsection of this that corresponds to 1 function call. So about 1 function call in Python corresponds to 7 stack frames in C, to 7 function calls in C. You have to call vector call, you call something else, and you call something else, and you call something else. And that number 1 call function, as you can see, the invocation of this, in this case, would be the invocation of HHH from GGG. So you can see there's quite a lot of work. There's quite a lot of splay out. 1 line of Python corresponds to many lines of C code. And you can think, well, function calls really are expensive. And maybe the speed of this function call is what's dominating the overall speed of this benchmark. And as a consequence, if I eliminate that entirely, then I'll see a significant speed up, which is why the pure comprehension works. And the other examples or why the pure comprehension is the fastest in all cases. And the other examples have some other different behavior. Now, this might mislead you because that might be the intuition that you get. Oh, if I want my Python code to be fast, even if the execution environment around me changes, I should avoid things like function calls. I should build some intuitions around what is fast and what is slow in Python. Things like function calls are slow, and I should just go ahead and use that intuition to guide how I write my code. Oh, is there an extra function call here? Then I better not use it. I'll try and inline as many things as possible. Now, the reason this might mislead you is that function calls aren't necessarily slow. Now, this is a somewhat weaselly sentence because it could be the case that further optimizations might take those 7 stack frames down to fewer than 7 stack frames. A lot of work has already been put into optimizing what happens in a function call in Python. Function calls are much faster in Python now than they were in previous versions of Python or in Python 2. And so that they're slow today doesn't necessarily mean that somebody couldn't go in and find some other fast paths to make them fast tomorrow. And this is only talking about some function calls. This is function calls where the underlying function is user-defined in pure Python. And there may be fast paths that you may have seen invoked already for function calls where the function itself is written in C, or it's a built-in function or something of that nature. Now, even though this is kind of weaselly, though, because in practice, in general, today, yeah, function calls are kind of slow. But and in practice, when we actually do benchmarks, we see they kind of drown out other slowness. But something is kind of strange here, because in the Python 3.7 example, we have 2 function calls. We call list, this value constructor, and we call map, this built-in function. And yet, this is faster than calling 1 function, map, and then unpacking this into a list. Now, obviously, some of this is going to be drowned out by the numerous calls to this f function, but still you wouldn't really expect number 2 to be the fastest of the two. Now, there might be some measurement error here. I ran this over a couple of samples, but something is kind of interesting here. One extra function call seemed to not really make a difference. And if we take a look closely what the bytecode is, in Python 3.7, this line is a call function, and it does invoke many, many lines of C, 7 stack frames of C. And the other line is a build list unpack. In Python 3.9, it changes slightly to a list extend bytecode. And in Python 3.9, this latter version is now slightly, barely measurably faster. But you can see, this guidance of, just avoid function calls would have failed us in this example because it doesn't really give us a clear indication of which one of these would be faster. Now, you could say, well, they didn't take into account the number of times this behavior was invoked, but still, there's something somewhat missing here. Fundamentally, I think a better guidance from this is the intuition that Python itself is slow, or maybe that invoking bytecode is slow, or maybe that doing work at all is slow. If you need to do some work, it's going to be slow. And an intuition you might have that's related to this is that dynamic dispatch is slow. Every time we have to perform some operation in Python, we do dynamic dispatch, and there's many, many lines of C corresponding to one line of Python, and this is where the slowness of Python comes. And we may have seen this before. When we multiply x and y, this gives you a binary multiply bytecode, which calls number multiply at the C level, which steps later calls long multiply to actually perform the multiplication if this thing happens to be 2 integer numbers. And if we have an addition, this calls not binary multiply, but in this case binary add, which calls number add, which eventually calls long add. And if these happen to be something like strings, it'll still go binary add, then number add, and then eventually some kind of string concatenate or list concatenate or tuple concatenate based off what it is. And you might say, well, this dynamic dispatch is adding many, many lines of C for one line of Python. And so one way that I could make my Python interpreter fundamentally faster is to eliminate this dynamic dispatch. This is the source of all of my worries, and that's my intuition. But in fact, if you take a look at the binary add code, you'll see that somebody has already gone in and added in this specialization. When you do binary add on 2 Python objects, if they both happen to be exact Unicode objects, you do a Unicode concatenate, and you do not do this dynamic dispatch. And so you might say, that intuition was actually pretty good, because that intuition is exactly why somebody added this line of code. But if you scroll up just a little bit above those lines of code, you'll see this comment. Please do not try to micro-optimize int plus int using bytecode. It doesn't work. It's worthless. It doesn't do anything. In practice, if you have ever thought, dynamic dispatch is the reason why Python is slow. And so what I'm going to do is I'm going to try to remove dynamic dispatch by adding specialization operations at my C eval loop level. Go ahead and try it. You won't actually get any measurable performance outside of synthetic micro benchmarks. And so it's not dynamic dispatch. This intuition that we have about dynamic dispatch being slow is, again, misleading us. Now, what we might think is, wouldn't it be nice if Python could do some kind of optimization? So if we have a function of f and it returns x, and I guess this function should have taken x as an argument, but you'll accept my apologies for the typo. Python can perform some optimization. It can do constant folding, and you'll see that in practice, what Python will do is it'll fold that 1 plus 1 into 2, and so it'll perform this very simple optimization to eliminate one unnecessary binary add. If there were another function g, and it called f, and it added 1 to f, unfortunately, what we might like Python to be able to do is to perform optimizations between the two of these to fuse them together. But unfortunately, Python functions are very opaque. And so there's not the possibility for the Python interpreter to perform this kind of inlining. And so we might say, this is another intuition. The reason why Python is slow is because we don't have the ability to perform cross-function inlining type optimizations. We can't have one function see into another function and see into that other function and then use some information that's available in that other function in order to perform optimizations. And that might be our guidance. And we might use that guidance to draw ourselves to tools like Numba. But for those of you who've actually used Numba, you can see Numba is kind of hit or miss. It is a great tool to use because you just add a decorator numba.jit to the top of your code. If it's faster, move on with your life. If it's not faster, figure out something else. But there's still something missing here because in practice, when we use numba.jit, I'm sure some of you have tried using numba.jit and you've seen no actual speed up on the underlying code. So just being able to add enough little structuring in so you can make these functions no longer opaque, but perform optimizations between them doesn't seem to be enough. Now, another thing you might say is my intuition is that loading variables in Python is slow. Load global is slow. And so if I have to optimize my Python code, what I'll do is I'll take load globals and I'll turn them into load locals. So I'll do these little tricks like hiding variables in keyword arguments. And you'll see this in the Python standard library. The inspect module, actually the JSON module does this in a couple places. And this was very much the case. It used to be the case that when you load a global variable, it was a dictionary lookup, and that was slow. And some optimizations have been added to speed up looking up global variables. If you ever look at the bytecode and you wonder why why loading a local variable is actually called load fast, is because an optimization was added there where loading a local variable in the Python bytecode is not a dictionary lookup, it's just a CRA lookup. And so there was definitely a case where somebody looked at that and said, oh, this is actually kind of slow. Similarly, you might have some intuition about method lookups, and you might say, oh, method lookups are slow. Every time I do an a.x, that's slow. So if I do that in a tight loop, it's probably a bad idea. So I should move that out of a loop. But method lookup was itself optimized in fairly recent versions of Python as well. And so some of these intuitions may only be timely around a particular view of how Python works as of when you learned that intuition. In the case of something like load global, you might say, well, the reason why this Python code is slow, even though it just calls len in a loop, is that every single time that loop goes, it has to look up that len variable in the global scope. And Python is so dynamic, and somebody could have swapped out that len variable, so it has to perform this lookup every single time, and that's a lot of redundant work that's being done. And you might say, wouldn't it be nice if Python had some kind of constantness like JavaScript has? And maybe if it had this kind of constantness, we could start to edge away. We could start to hedge ourselves against some of the dynamic nature of Python and perform these optimizations. This is something that I haven't seen a lot of people try in trying to improve the Python interpreter itself. It is something that I would be very curious to see how it works, but I would be somewhat surprised if you saw significant speedups because areas of Python that people have seen that are slow, like load global, have already had some work put into them. You might say that this is actually a very similar optimization approach to something that you've used in practice, PyPy. You can think a tool like PyPy figures out, oh, there's fast paths and slow paths, and so if len doesn't really change, the fast path will assume that it doesn't change, and it'll perform some kind of jitting. And based off that jitting, we'll be able to eliminate redundant operations. But if we're wrong about that jitting, we'll go down a slow path and look it up. And so we get the same behavior with faster performance. In practice, I don't know that I've actually seen PyPy in a very similar way to Numba guaranteed provide performance to code. And unfortunately, one thing that we see about PyPy is the support for tools like NumPy and Pandas. Without that, it's really a non-starter. What I would say fundamentally here, our intuition, should not really be built around, oh, this particular structure is slow, method lookup is slow, load global is slow, Python function calls are slow, so much as each one of these are missing some kind of structuring. And in the absence of this kind of structuring, we have no choice but for this code to be slow. This brings us to the next letter, the S for structure. And this is where we want to spend the most of our attention, the most of our time. When we talk about Python and making Python code fast, one of the topics that sometimes comes up is generators. And for those of you who are data scientists and not data engineers, you might have seen some examples of generators where they're doing some kind of data processing, and you were very unimpressed. You saw somebody write some code where they had a generator that squared a bunch of numbers, they applied it to a range of a bunch of numbers to build a list, and when you actually looked at it, you said, you know what? That is kind of cool. The generator is kind of a cool structure, but you know what? I just use NumPy, and the code is shorter, and it's a lot easier to read. And if I actually measure this, the NumPy code is way faster. And you know what? I didn't even measure this fairly. I just measured the whole block, not including the setup. So the NumPy code is way faster, including the construction of this 1 million element NumPy array. In the case of the comprehension syntax with the generator, that range object is not a concrete collection. And so this is a very unfair comparison. And even in the unfair comparison, the NumPy code is 200 times faster. And so when you look at that, you might say, come on, like, don't start telling me about generators in terms of optimization. This is clearly adding nothing to my Python code. NumPy is how I do fast computational code in Python. Generators are just a non-starter. They're cool, they're fun to read about, but they don't actually do anything to make my code faster. But I would argue that you are very, very wrong. And the reason I would argue that you're very wrong is, what if your code looked like this? You have a generator, you perform one square, and then you break and stop performing the operation. Fundamentally, what's making your code slow is that it has to do some work. If you didn't do any work, then the code wasn't slow. Fundamentally, those NumPy operations are eager. And so even if you didn't look at all the values that were being performed, it's fairly difficult for you to say, oh, only perform the values as I ask for them. And in this particular case, this generator code is actually significantly faster because it doesn't do anything. And if you think about that, you might say that's very synthetic. Like, okay, what's the point? But when you start to think about this a little bit deeper, what you can think is the generator structuring actually allows you to control how much work is being done. And if you can more precisely control the amount of work is being done to match to the work that needs to be done, you can sometimes find optimization, because it is fundamentally the case that for the most part, doing less work is going to be faster. Now, that's not always correct. So don't be too misled by that, because we have seen cases where, as a consequence of CPU speculation mechanisms or confounding factors like branch misprediction, it is sometimes the case that doing extra work is faster than having to encode a modality. In other words, you have almost certainly seen a case with a NumPy and D array where you performed two operations and a conditional, and instead of choosing which of the two operations you wanted to perform with some kind of modality, some if-else, you found that it was faster to perform both of them simultaneously and then just multiply 1 by 0 or multiply 1 by 1 and then add them together. Because what you can think is the speculative units of execution inside your processor can perform both of these in parallel and just throw away the work. And if you think about CPU speculation, you can think, oh, in many cases, that's exactly what happens. It's oftentimes faster to go ahead and do work and throw it away than to try to wait to figure out if you need to do that work or not. And so this idea of doing less work is necessarily faster or better than doing more work is not quite correct. It needs a couple more qualifications than simply that. But for the most part, if you can control the amount of work that's done, for the most part, at the macro scale, you'll probably see some kind of optimization. And this is what generators give you. And this is why generators are such a powerful mechanism for optimization, even though you almost certainly have never used them as a computational entity in any of your NumPy or Pandas code, and you will never use them as a computational entity in any of your NumPy or Pandas code. What you will use them for is program structuring. And this is the most critical part. Let's say you have a piece of code, and it has three functions in it, f, g, and h. And your program is the composition of these three functions, f, where you call h on your data set, and you call g on the result of that, and you call f on the result of that. And if you think about that, what does f see? Well, f sees some concrete result. What does g see? Some concrete result. And only h sees the initial data set. Because functions as a unit of computation are fundamentally eager, composition of functions can't see that composition of functions exists. There's not sufficient program structuring. If you were to instead think of these as two functions like select and process, and you were to say, okay, here I do some processing of some data set, and I do some selecting of those data sets, you can see there's probably a problem in this code. You do the processing, and then you select the items from that processing that you want. If that selecting operation was not or did not require something that was computed by that processing, you might find that selecting might actually eliminate items that you spent time processing. This is a very common problem. If you've used Hadoop, you've seen this problem before, and you may have seen it called predicate pushdown. It is very much the case in query optimization tools that oftentimes when we have a select and a process, we want to take that select and push it down as far as possible to eliminate items for processing as early as we can to reduce the total amount of work that we need to do. And in the case of these two being written as functions, unfortunately, we can't do that. The select function sees the result of that process function, and it can't perform predicate pushdown. This is impossible. But this is where generators are such a powerful technique. What you could do is you could say, oh, my process is a generator, and my select is a generator. Now, by themselves, this doesn't do anything. But you could say, my process is a generator. For each element of the data set, we perform some function on that. And I'll just add a little decorator called tag to it. And I'll call this a map operation. And then I'll say my select is a generator. For each element of my data set, I'll perform some condition on it. And if I meet that condition, I'll yield that element. And I'll also tag this. I'll call this a filter. And this might not seem very interesting. Like, what is this decorator? We have to probably write it ourselves. What does map? What does filter mean? Well, if you think about it, we could write this decorator like this. What it does is it creates a class called gen, and it wraps the generator and just stores those tags somewhere. Just stores that information that you had there somewhere. And when you call this class that you defined here, all it does is it invokes the generator to give you the generator instance with the arguments. So this didn't really do anything. It stored that information, didn't use it for anything, didn't go anywhere. But then you might say, you know what? Instead of returning that raw generator instance, what if I mock out that generator instance? What if I create my own instance type? And what I'll do is I'll have its next just called the next on the generator instance. And in the iter, I'll just create the generator instance. But in the iter, which gives me that generator instance, what I'll do is I'll look at the tags and I'll do something with the tags. I'll see if I have a filter and a map. And if I have a filter and a map in that particular order, I'll perform predicate pushdown by swapping them. The generator here is giving you some kind of program structuring. Because those two generators exist at runtime, and because they are lazy computational units, because they're computational thunks, they can see each other. Because they can see each other, they can operate on each other. Because they can operate on each other, that program structuring that is now created by that generator structuring that you have can be used to do things like predicate pushdown, which can then lead to optimizations later. In other words, your first optimization might look like this. If you have a filter and a map, and it's a filter being composed with the map in that particular order, swap the order. So you do the filter first and the map second. And obviously, in this particular case, we don't have enough structured information here to know if this is safe or not. Maybe the filter requires information that was created by the map. But obviously, you can think, if you wanted to extend this example very slightly, you can encode a little bit more information in this in order to be able to determine whether this predicate pushdown could be done or not. Now, what's very interesting here is I have shown you how you can do predicate pushdown in Python using generators in about 2 lines of actual core computational code and maybe 15 lines of structuring code. It's a very, very simple framework, and it probably won't work for many problems, but you can think even this simple framework shows you the possibility of generators as a structuring tool leading to optimization. And the underlying computational elements that you work on can still be your NumPy ND array, but the program structuring element that then structures that program to eliminate redundant computations that are then performed within that computational domain might make use of this generator structure. Now, you can think you could do some very interesting things here. You could say if the generator itself is the process generator and the argument to it is the select generator, swap them out, fuse them. So perform some kind of generative fusion. You can't do that on functions. They compute eagerly. But on generators, because they compute lazily, and because they give you the actual structure, they give you that information that's retained, you can do some very fancy things. You can swap out f of g for some fused version that's written in C that's highly optimized for the particular problem that you're solving. And so even if f and g happen to be elements that themselves use pandas or NumPy for their actual computation, because you've built the structure of your program in this way, you can perform optimizations that then take combinations of NumPy operations or pandas operations and elide operations that are unnecessary, or swap out specific operations for operations that might fuse things together. Now, this kind of program structure you may have seen before. And you may have, and when you think about it, you may have seen this kind of program structuring before. And before we get to that, I want to talk a little bit about what I mean by the overall program structuring. So when you think about the code that you write, you might think about the code as having some core to it. And you might call that core some root. And there's some portions that extend from that root, and there are some leaves. When you think about your code in this way, you might say, well, oftentimes I have areas of high churn and areas of low churn. At the root, I have low churn, ideally for a well-produced piece of software. I have low churn at the root, but I may have high churn at the leaf. And in fact, I may even design my program so that there's very high churn at the leaf to limit the amount of churn that I have at the root. In other words, what you might think is that at the root level, you have some kind of program structure. You've decided, I need to encode certain guarantees about the way that my program works, or certain information that can then be used at the leaves in order to perform micro-optimizations. In our first view of the micro-optimization, we were guiding this with just measurements. And we didn't really think about it in terms of the structure of our code base. One of the problems that we saw with those micro-optimizations are no longer valid if the execution environment around you changes. But if we think about software programming as a dynamic process, it is always the case that our code base will change. There's always going to be some churn. If we isolate our churn to the leaf level, because that leaf level has no further dependencies, it's a very safe type of churn to have, and it's a very common type of churn. And so if we limit our micro-optimizations to that leaf level, even if it's the case that those micro-optimizations change over time, we might just have to revisit them every so often and then see which ones work. If those micro-optimizations occur at the root level, we could lead to some problem, because we might end up rewriting code fundamentally at the root level that causes downstream problems, that causes a lot of churn in the pieces that depend on that. And so what we generally want to have the case to be when we design our program is that we have some fundamental program structuring that exists at the root of our program that makes it possible to do micro-optimization at the leaf. If you think about that predicate pushdown formulation, that was program structuring at the root. We structured these computational entities as generators, and then at the leaves, we perform some kind of fusing or some kind of predicate pushdown or some other kind of optimization. And this, in practice, tends to work well. If you think about this kind of generator structure, you may have seen it before. If fundamentally in this generator structuring, what we're doing is we're making these computational entities first class, then we can manipulate them later. You might have seen this in the form of a computational DAG. Instead of executing some computation, you construct a DAG, and then you selectively re-execute portions of that graph as those portions get dirty. In fact, you may have even seen a framework like Dask that gives you the ability to exploit this kind of structuring information to pick the most efficient execution backend. And so this is actually a fairly effective way to write Python code in a structured fashion that will lead to optimizations at that leaf level. And it's a much more effective way to think about this than thinking about it in terms of these very simplistic intuitions and then trying to just put number.jit all over the place. But this program structuring goes a little bit deeper than just that. It is a very successful approach for high performance, but there's another type of program structuring that you might see. Now, before we get into that other type, I want to just kind of recap for you the general approach that I'm suggesting. Use program structuring at the root of your program. This encodes important structural information, like I have some composition of functions. Because you've encoded that information, you are then allowed to exploit that information to eliminate redundant work or to perform some kind of specialization on that work, like fusing two function calls or two generators into a fused hyper-optimized C version. And this is how you exploit this structuring to gain performance at that leaf level over the long term of your project itself. There are other program structurings that you may have seen before that are similarly effective. Let's say that you have some program, and in that program you have individual data items, and they're represented as Python objects, as single Python objects. And your data set is just a Python list of these Python objects. It's a very simple modeling of a problem. Now, obviously, if you're a Pandas user, you might skip this step entirely and go straight to Pandas, but let's pretend that you're starting with the very basics, and you're trying to reach for as little as possible in your Python interpreter, as little as possible even from your standard library. So you might start with something like this. And the moment that you need to scale this up to 10 million items, you might see the memory use is very high. The reason the memory use would be very high is that this individual class object has a dict object associated with it. And if you look at the size of this thing has 64 bytes in size. Python dictionaries are very large, and so Python classes, instances of Python classes are very large, so they carry this information around. But that datum doesn't really have that much information in it. In fact, it has no information in it. And so you can see paying 64 bytes for each individual datum, it's going to blow up your memory, and you're not going to be able to scale this. Now, you might say, well, an easy way I could do this is I could use like a name tuple. And so the name tuple is a little bit smaller than a custom Python class. It doesn't have that dict on it. And so I will see a performance benefit. Or you might say, let me use slots. The moment you say, let me use slots, you're going down exactly the wrong path. I would argue that the reason that I put this talk together is basically for the purposes of just this one slide. I hate talks about slots. Slots is not a useless tool. It is useful in a particular niche to accomplish a particular goal, but it is way overhyped, and it is an incredibly misleading approach to optimization in Python. If you have a system in Python and you're seeing it's slow, my memory use is out of control, and maybe it's slow because the data items in Python are allocated on the heap, and so they're not contiguous. And so if you're doing some kind of aggregate operation, some kind of broadcasted operation, or vectorized operation, you can't perform, you're doing multiple memory lookups that aren't cache coherent. So you're making no use of your L1 cache because you're jumping all throughout memory to load this up. So you may have seen that problem before. Slots doesn't affect that at all, but at least it'll affect the size of this thing. And so maybe if you're lucky and these things get allocated next to each other, they'll at least be packed close enough to fit into a cache line, maybe. Fundamentally, when you think about slots for optimization, you're going down the absolute wrong path, because slots has never, ever made somebody's Python program meaningfully less intensive in terms of memory. There is another approach that is much more successful for this, and the approach looks like this. Instead of looking at slots, which won't help you, because even if you use slots, you still have a Python object. And if you have a Python object, you still have to store a lot of additional information, even though this is just a very small data item. You have to store a pointer to its ob type. You have to store its ref count. If you have this PyHead extra, you may have to store the linked list as well. It's quite a lot of information you have to store. You end up being boxed in. And this is something of a pun, because fundamentally what you're dealing with are box types. And when you think about that, you might say, well, hold on a second. This is why languages like Java have boxed versus unboxed types, because the box types are fairly intensive in terms of the amount of memory they use, and this has some other consequences in terms of, things don't fit into cache lines anymore. Now, if I showed you some code that looked like this, multiply these entities, and we park this question of the size of these objects for a moment, we might say it would be very nice if this kind of multiplication could be automatically parallelized. That could lead to some kind of performance. We have multiple cores, we have multiple ALUs, and if we could parallelize this, we could do more work in the same unit of time. But the problem is, and you may not be able to see this code too clearly, but the problem is that if this code is written in Python, and these are Python objects, these Python objects could have any arbitrary behavior. In this particular case here, I have an object, and this object has the ability to mutate objects that it's referring to while it itself is being added. So you add 1 to some object, and because it has a reference to some other object, it goes and mutates this other object. Because that is not visible to the Python interpreter, and the Python interpreter cannot see that, Python interpreter can't say, I'm performing the summation, if I change this object, it has no effects outside of this object. Python interpreter does not have enough structural information in order to determine that. As a consequence, the Python interpreter cannot naively auto-parallelize any sort of aggregate operation, because it necessarily has to do them in the order that is specified lexically, in the order that you might specify it with a naive execution model, because you can have these weird behaviors that somebody has added to their classes. And so what you might instead do is you might say, you know what, instead of having these in a list, I'll put these into a custom class called a data set. And in my data set, I'll just store the data items. And then, you know what, I won't drop into pure Python code. I'll have these operations on the outside of my data set, like inc, to go through the data set and increment everything. And when you do that, you'll see, well, nothing's really changed. I'm still using the same amount of memory. It's still as slow as ever. But then you might say, you know what, why don't I just use Cython? And I'll swap out this class with a version in Cython. And the moment I do that, I say, you know what, why am I doing self.data equals data in Cython? Why don't I just extract? Why don't I unbox these Python objects and store them contiguously in a C array? And when I do that, I end up getting some very interesting benefits from this. They're stored contiguous in a C array. So when you're performing aggregate operations later on in your Cythonized code, you can now make use of things like cache coherence. They're much smaller in terms of their use because they're now packed to whatever the smallest amount of space that's needed in order to store that data. And because they're cache coherent, when you're performing operations on these, you're not seeing a lot of cache misses that are leading to very poor performance. You might also be doing, you might be adding restrictions. Because you're saying, oh, my little data set class here is taking these objects and unboxing them. And because it's unboxing them, some of these custom behaviors can't be preserved. And so what I'm doing is I'm adding a restriction that these custom behaviors can't exist. And if you think about this a little bit, you might think, haven't I seen something that looks like this, like a dataset class where the contents are required to be machine typed, they're required to be contiguous in memory. Because they're machine typed, there's no dynamic dispatch on these, and there's no interdependencies. Hold on a second, that's a NumPy ND array. This is what a NumPy ND array is. The NumPy ND array is the idea that you can create a restricted computation domain. That restricted computation domain gives you the ability to store items in an unboxed fashion so that they are optimized for the operations you want to perform. Boxing and unboxing happens at the edges of this. So whenever you actually do an indexing operation on the ND array, it'll take the C int and give you a Python int. And remember, the ND array integers are not Python integers. They're int 8s, int 16s, int 32s, or int 64s. They are machine typed ints. When you perform an operation in ND array, you don't say for x and ND array perform something. What you do is you say ND array do a dot sum. And it figures out how it wants to do that sum. And because it has drawn a line around this data set, and inside of its own controlled access to its own contents, it is able to then perform optimizations subject to whatever execution environment that it finds itself in. Optimizations such as, instead of doing dynamic dispatch on every binary multiply or binary add, I'll just use an IAdd or a FAdd. I'll just use the exact assembly language instruction, or I'll use some AVX instruction instead. In fact, this is a pattern that you may have seen many times in many places. This is the general idea of a restricted computation domain. This is probably one of the more common and most successful approaches for optimization in Python. What you see is if you have a program, and that program interacts with many data items, and those data items are starting to blow you up in memory, and they're not cache coherent, so computations on them are slow. What you do is you draw a line around those data items. You call it a manager class or a dataset class or a NumPy ND array or a pandas data frame. You call this a restricted computation domain. It's a restricted computation domain because it's a little domain in which the computations are performed. You no longer extract those objects back into boxed Python objects. You perform all the computations inside that domain. You always do NumPy ND array.sum or pandas column dot whatever. And you know from when you're dealing with pandas, anytime somebody does something pandas iter rows, or they do a dot apply or any operation that pulls the data out of pandas, it's always slow. Well, this is the reason why. As long as you're inside the pandas computation domain, pandas is able to exploit whatever tricks it can figure out to make the code inside of it fast. The moment you pull this out into generalized Python, you no longer have that ability to exploit that information. In the generalized domain of Python, there's too much dynamicness and too much freedom with what you're able to do. Within the NumPy ND array, well, these are machine-typed floats. There's no interdependencies between them. They're, adding two of these has a very well-defined behavior that can be implemented in a single assembly language instruction. I can make full use of my multiple cores, my multiple ALUs. I can make full use of my vectorized instructions, and everything is very compact because I store just enough information that I need. If you think about some tools in Python that are very common but very slow, think about something like NetworkX. NetworkX gives you the ability to represent a graph. And if you ever use NetworkX, one of the problems you've seen with NetworkX is once you get to a graph of a particular size, you start running out of memory, and everything, pathfinding and other operations become very slow. Why is that? Well, Network X's modeling of the underlying graph is of a dictionary, dictionary, dictionaries. Network X does represent a restricted computation domain. They just haven't gone the whole way. One of the things that they want to do with Network X is make sure that you could always import it into a Python project. You didn't have to have any C dependencies to build it, so it was pure Python. And as a consequence, they weren't able to take this all the way. But if you think about it, the Network X digraph or graph object give you the ability to draw a little line around the underlying objects that are contained, the edges and the nodes. Inside that Network X, if somebody wanted to perform some optimizations, what they could do is they could eliminate the ability to pierce that veil. They could swap out this dict representation, and they could start storing things in a more compact, more optimized fashion, more specialized to the actual problems they're solving. Now, unfortunately, in the case of Network X, this wouldn't be as easy as I'm saying that it would be, because people still have certain assumptions around the way the Network X digraph or the Network X graph is used. Certain assumptions like the nodes can be any arbitrary Python object. And what you've almost certainly seen is if you try to create a NumPy ND array that contains Pi objects or a pandas data frame that contains Pi objects, you see that the performance there is not meaningfully better than just putting it into a Python list. This only really works if you're able to put sufficient restrictions around the domain. And so in the case of Network X, the idea wasn't taken all the way because maybe there weren't enough restrictions that could be added without significantly degrading the generality of the tool itself. Now, if you think about this, what you can think is that generally the process is you have a bunch of data items that are individually boxed, and then you just kind of box them up with some domain. You put restrictions around them. You exploit those restrictions. And so this gives you something like the NumPy ND array or the pandas array, series, and data frame. Now, if you have some code that looks like this, you have some data set, you process this data set, and you process this data set again. So you do two operations here. Even if you were to create a restricted computation domain, like you were to switch this code here into code like this. And so instead of performing these operations in the Python bytecode with this list comprehension syntax and a function call, you're to perform them inside the domain. You're still going to run into trouble because in between the creation of YS and ZS, there's a temporary. And you've seen this in NumPy, and you've seen this before in larger computations. There's temporaries that are created, and they use a lot of memory, but you don't ever really do anything with them. And unfortunately, there's not enough program structure information here in Python for Python to know, YS is only really used in this program in order to create ZS. And even if we chain these together, still we create the result of this first operation and then the result of the second operation. And so even if we chain these, we don't really get anything because one temporary is created and that temporary is used. And unfortunately, there's not enough information here because these are functions, not generators, to let us know, oh, let's stack these operations or few these operations. And so there's still some issues with this computation domain. Well, one of the things you might try and do is you might try to find a way to fuse them. So you might try to add that programming information. And so one thing you might do is you might say, instead of having two individual Python functions that I call in some chained fashion, I have one function that I encode the chaining of these operations as a string. This is basically NumPy einsum or numexpr. All it is the idea that you don't have sufficient structuring information in your code in order to see how these two operations are being performed in order to remove or elide temporaries in order to do less work. And so NumPy einsum is a very popular tool because it gives you a string-based language for defining transformations on a NumPy ND array. numexpr is the very same thing, string-based language for defining operations on a NumPy ND array. And because it can see the entire operation as a single entity and it can build an AST from it itself, and it has that program structuring information, albeit provided in a fairly clumsy API, it's able to then perform those optimizations later. And this you can see as a root level choice that then leads to leaf level optimizations. This leads us to our second S, specialization. And I don't want to talk about this too much, but I do want to just draw your attention to the idea that optimization fundamentally is specialization. In other words, let's say we have a NumPy program, and it takes the numbers from 0 up to, but not including 10, and it sums them together. We can perform some optimizations on this in order to make this faster. Like NumPy A range is never going to change. The sum of the values from 0 to 9 is never going to change. We could perform an optimization, or we could perform some kind of specialization, like say, oh, these are specifically int8s. Now, in the case of NumPy, that's not a really big deal. But if you compare this to like the Python program where they're ints with automatic promotion, yeah, from ints with automatic promotion to int8 reduces a lot of extra work that you have to do. But an even better specialization would just be to reduce this program to the number 45. Very, very smart compilers like the Haskell compiler can do this. They can see, oh, these are constant expressions, and I'll just reduce the entire program into a single constant expression. Python is not able to see it because it does not have sufficient structuring information. It can do constant folding in some very, very limited cases, but even constant folding like string operations are just too opaque for Python to be able to see. What you can think is specialization fundamentally requires program information. And Python, by virtue of its dynamic nature, has very limited ability to provide that program information. But if you think about this, what you really want is not just program information, but program structuring. When you think about Python, you can think, well, this is why Python is slow, because it doesn't really provide us, it's too dynamic, and it doesn't provide us this program structure, this program information. It's too dynamic. Maybe it provides us some kind of structure or some kind of information, but things are changing all the time, so we have to repeatedly check things, we have to repeatedly do dynamic dispatch, we have to repeatedly look things up to see if somebody swapped out our len function for us. But another interesting thing about Python is very humane. And so what we can see is that Python is actually a very rich language, a lot of rich metaphors that are provided to us. These rich metaphors are things like generators, the object model, or context managers. These rich metaphors are very easy to use. In 15 lines of code, I can build a framework for you that uses generators, that gives you just enough information to do some very, very sophisticated things like fusing of computational units, that can build things like a graph framework. In a previous talk called More About Generators at PyData London 2017 or 2018, I built a DAG framework in about 45 lines of code using generators. Obviously, it was a toy framework. Here, in this case, in about 15 lines of code, I built a predicate pushdown framework for you in Python. Obviously, again, it was a toy problem. But you can see these metaphors are very easy to use. Very little code. You can expose enough human-level information, structuring-level information, to then employ to get ad hoc structuring that leads to optimizations. And so what you can think is, at the root level, what you want to do is you want to use the fundamental humaneness and the fundamental program structuring mechanisms provided to you by Python to encode structured information. At the leaf level, you want to exploit the structured information. And then, even if things change around you, you will have built into this process the idea that at the leaf level, as long as certain assumptions that are still met, and these may be more fundamental assumptions like the less work that I do, the less time that it takes. Those are assumptions that are less likely to change over time. Obviously, we don't know what computers will look like in 30 or 40 or 50 years. And so over the very long scale, some of those assumptions at that root level may be wrong, but we can generally make educated guesses about what they might be. And those educated guesses may survive much better than the kind of guesses we saw when we were trying to micro-optimize single lines of Python code. At the root level, we encode structured information. At the leaf level, we exploit the structured information. We structure that information based on some intuition, but not really, because the problem here is our intuitions are not always right. Maybe we make use of broad intuitions like doing less work is better, or being able to see what you're doing is better. And so it's not really structuring it based on the intuition so much as structuring it based on the problem. We say, these are the aspects of my problem, the facets of my problem. These are the aspects of my problem, like we're doing some kind of composition and we want to, and some node and some graph becomes dirty, so we want to do the minimal amount of computation. So we need to be able to track when something is dirty, when something's clean. We need to track and build that DAG for us, something like what Dask does or other frameworks do. And instead of basing that structuring on intuition, we create structurings that lead to better intuitions. When you use NumPy and pandas, and you'll see a talk later today about optimizing pandas, one of the things that you might see is well-designed libraries in Python that provide the structured information lead to clear intuitions about how to use them. And so if you know a couple of rules about pandas, like stay inside the pandas data frame as much as possible, avoid .apply because that pulls you out of the data frame, avoid .groupby because .groupby has parts that are written in pure Python. In fact, just kind of avoid dumping into Python, try and keep everything inside the pandas array or ND array backend as possible. Just that gets you about 90% of the way to faster pandas code. And you can see, I wrote some pandas code in order to do the performance analysis for this. And the pandas code had some areas where I said, can I do this inside pandas or I have to drop out to like a Python loop? And in some cases I said, you know what, it doesn't matter if I drop out to a Python loop because I'm only iterating it 3 times. But in other cases I said I should stay inside pandas because I'm iterating it for the entire data set. And so if I think about this in terms of my asymptotic complexity, I might say asymptotically I want to always try and stay inside the restricted computation domain. The structuring that was provided to me by that tool led to that intuition, which led to a very good guide in general for these optimizations to work. And so what I want to leave you with at the end of this talk is that when we look at successful optimization techniques like Dask or NumPy or Pandas or Numba or anything that you write yourself, it's not about slots. It's not about jitting. It's about a particular conceptual framework. And that framework is you want to separate your code at the root level and the leaf level. At the root level, you want to encode structuring information that leads to optimizations at the leaf level. And I've shown you 2 of those kind of structurings. One of them is making visible in your program the computational units using a mechanism like generators. And because you make them visible, then you can perform optimization at the leaf level to fuse them, to align them, to swap them out, or making use of this restricted computational domain pattern. And so, you draw a red line around your data items, and inside that data items, you add some restrictions, and you say within that restricted computation domain, we do whatever we want to make this as fast as possible. We might swap out our internal code. So the numpy and array.sum might swap out over time. But for the most part, from the high-level view of this program, we just call it .sum. The code is readable. And inside the computation domain, we figure out how to perform those micro-optimizations. And so given this framework of MISSI, I hope that you've gotten a better sense for how to conceptualize what optimization is all about in Python, what makes Python code fast or slow. I hope this has managed to dismantle some or disabused you of some misapprehensions around, or some mistaken views around what optimization means or what you can do to lead to Python code. Yes, it is the case calling Python functions is slow today. Will that be the case in 2 years, 3 years, 4 years, 5 years? I don't know, probably, but I couldn't say definitively. And I wouldn't necessarily want to use that in order to guide myself to better code. What I'd want to use to guide myself to better, faster code would be exploiting underlying structuring information, making use of the features that Python has to offer. And so when you think about optimization in Python, always come back to this MISSI framework, where MISSI stands for my. Isn't structuring surprisingly important? I'm James Powell. Thank you very much.
Thank you so much. That was really inspiring. Great. So I think I saw some questions already pop up in the Discord. Maybe there's also some questions here in Zoom. I also have some questions myself, because do you know of whether there's any of these restricted computation domain initiatives for graph libraries out there?
So I have a study group that has been researching better graph implementations. We're on sabbatical right now, given the current circumstances, but we're trying to look into whether it's possible to write a better tool than NetworkX for higher performance graph computing. Mm-hmm. The limitation is, one of the great things about NetworkX is it's pure Python. And so you don't need to use Conda, you don't need to build anything. If we're willing to release ourselves from that restriction, it should be fairly easy to write something that gives us better behavior making use of this. Now, there's some other issues with NetworkX that are separate from the performance aspect, like that it doesn't have copy on write, that it doesn't give you the ability to create immutable graphs, that it doesn't have that the algorithms that are implemented are too opaque, and that the API is kind of matplotlib. It's kind of old. But those are something separate from the idea of like NetworkX having a restricted computation domain. There are tools like if you look at GraphTool, which is written in C++ with Python bindings, it gives you some high performance C++ backend. The thing is, it's just impossible to build. I tried to build it once, and I ran out of on a machine that had 8 gigs of RAM, and I ran out of out of memory just building the thing. So I think you can find something that's got the same ease of use of NetworkX, but you swap out the backend a little bit better.
I also see in the chat indeed, GraphTool is unbuildable.
Is it really unbuildable?
Yeah,
I think
someone else tried it as well. Yeah.
Okay.
Interesting. So graphs are indeed a very good use case of these restricted computational domains, I guess. Do you see other obvious examples?
Yeah. Anytime you have a program where you have lots of Python objects floating around and it seems to be getting slow and you seem to be using a lot of memory, that's a restricted computation domain. Put a little manager class around it, and then put enough restrictions, do some kind of boxing and unboxing on the inside, to pull things in and out of the computational domain, and then as necessary, add optimizations.
Okay, that makes a lot of sense.
I think it's a general pattern. Now, obviously, what you'll probably do in practice is your manager class will probably just use a pandas data frame or a numpy and array. So it itself will just make use of an existing one. Yeah. And that's what I see as a very common pattern. You have individual items representing the business entities, and then you decide, I'll put them in a manager class. I'll have the manager class use an numpy and array or the pandas data frame. The user of your code doesn't really know that the backend is a pandas data frame or an numpy and array. They just see the individual entities that are boxed and unboxed, and they just get some aggregate operations.
That makes sense. One of the questions from chat was about the map filter example with the tag decorator. What the trade-off is there by writing it sort of in that push down way versus the straightforward way?
The example itself is somewhat synthetic. And so what makes it somewhat synthetic is you're assuming that you're able to do this kind of predicate pushdown. A predicate pushdown is a very common thing that you see in SQL query optimizers. But it does require quite a bit of structured information. There was some sleight of hand there in that you can't really swap the map and the filter unless you know for certain that that's correct. And you need quite a bit of information added to the program in order to be able to make sure that's correct. So in this example, I just kind of shrug my shoulders and say, look, imagine that you have that information. Imagine you can add that in because it's not too hard to add that in. Now, in terms of disadvantages that approach, I don't know that I could really come up with a specific disadvantage. Fundamentally, it's just a different approach for writing code. Instead of writing them as a composition of functions, which no longer give you enough information about what's happening at runtime, you write them as generators. Now, I wrote this example, and I shared it with Tom Caswell from Matplotlib. And I shared it with him a couple of weeks ago, because this came up when I was doing a Python training, and I threw some code together, and I thought this is pretty cool, so I showed it to Tom. And Tom shared with us that in his work at Brookhaven National Lab on NSL2, they've actually built a generator framework very similar to this. And so while I haven't seen many approaches like this in practice, it is the case that people are doing things like this. And so it might be useful at some point to get Tom or Dan Allen from Brookhaven to talk about the generator framework they've built, because they've built a very similar framework for representing the experiments that their scientists are doing on the laser and then performing some kind of optimizations on that experimental flow.
That's really cool. Do you know whether that's open sourced or?
Brookhaven is an open site, so none of the work they do, I think, is classified. So I don't know if the code itself is open, but I don't think there's any restrictions for him to talk about it.
Talk about it. Okay, that's a good one. Definitely reach out to him. It sounds really interesting. Cool. I don't think there's any other questions from chat or Q&A as far as I can see. So yeah, well, thank you again for this talk. It was really nice.
Thank you, everyone. Thank you, Matthias and Mauricia, for putting this event on. Really appreciate you putting in the hard work to make this possible.
Yeah, you're welcome. These kinds of things make it worth it. So glad to have done so. All right. Well, with that, I'd like to say goodbye and see you next time, James, at the next virtual PyData event. I guess must be a bit easier to attend them all this year than last year.
Yeah, it might be. So I'll see you all at PyData Global. Thank you, everybody.
Thanks. And thank you to all the attendees. Hope to see you again either during the lunch session or this evening's talk session. All right.
Thanks, everyone. I'll stick around for a couple of minutes in the Discord if you have any other questions. Otherwise, it was a pleasure. Really my pleasure speaking with you, and I hope you enjoyed this presentation. Thanks, everyone.
Awesome. Thanks.